In this video, we are going to consider the properties of an Arch1 process. Before doing that, we start by looking at the framework of time-varying conditional variance as opposed to the error term, which is usually assumed to be a white noise process. So consider an epsilon t term, which has the multiplicative structure zt times sigma t, and zt is usually assumed to be an independent, identically distributed process with following some distribution, say a normal distribution with zero mean and a unit variance. And we also assume that the sigma squared t, or time-varying conditional variance, is a function of the past filtration only. So no new information at time t and determines the sigma squared t. Everything is determined by the t-1 period. And before we start with an Arch1 process, it is useful to think about this general framework and consider the properties of epsilon t. The expected value of epsilon t is given by the expected value of zt sigma t, and as zt is identically distributed term, we can split the expectation of the product into the product of expectations. And as we have assumed zero mean and the unit variance, we have that the unconditional expectation of the epsilon t is given by 0. Quite different is the concept of a conditional expectation. So we can also consider the expected value of epsilon t given the particular realization, given the particular filtration ft-1. So given that you have observed some return process up until period t-1, what do you expect epsilon t to be in the next period? And again, we write down the definition of epsilon t. ft-1 here denotes the information set available at time period t-1. Note that in the whole Arch framework, the sigma squared t here is a function of the past filtration only. So if you have ft-1, you can literally pinpoint what is the sigma t. And so you have sigma t being a deterministic function, and then you have the expected value of zt given ft-1. Now again, zt is an IID white noise process, so we have here only, again, sigma t times the 0, which is 0 in general. Now we look at the variance, the conditional variance of the epsilon t. It is given by the expected value of epsilon t squared given ft-1 minus the squared expectation. The conditional expectation, as we just shown, is equal to 0, so we are left with the expected value of zt squared times sigma t squared given ft-1. And again, as we assume that sigma squared t is determined by the ft-1, the information set available up until t-1, we have sigma squared t times the expected value of zt squared given ft-1. Now, what is the variance of zt? It is expected value of zt squared minus the squared expectation. And so the expected value of the zt squared, if the variance is 1, then the expected value of the zt squared is 1 as well. So you do have sigma squared t here times 1. And again, this you can pinpoint if you have the information set ft minus 1. Now, when it comes to the unconditional variance of the epsilon t, which we will denote from time to time as sigma squared epsilon, so this is unconditionally of the return realization, unconditionally on any information and data you observe. So in general, over the whole sort of probability space, how would you compute the unconditional variance if you have the knowledge of the conditional moments? Of course, you use the law of total variance, and you know that the unconditional variance is given by the expected value of the conditional variance plus the variance of the conditional expectation. And so we have now the expected value of the conditional variance, which is given by sigma squared t, plus the variance of the conditional expectation, which is 0. So we will denote the unconditional expectation of sigma squared t process as sigma squared epsilon. We now assume some structure onto the sigma squared t. So imagine that your daily return process is given by some conditional expectation of this return process plus epsilon t. And this could be your sort of ARMA guy in there. And what we are going to work with is a residual of this ARMA process. So the difference, the d-meaned return process essentially. And then we say that our epsilon t is sigma t times zt. For simplicity, we can assume that the expected value of the return process given ft minus 1 is 0, which is quite close to the what you observe in practice. So the returns, they fluctuate around 0 in general. And then your return process is just your epsilon. However, if you do not want to make this assumption, all of the properties of the arch process still go through. You just think of epsilon t as the ARMA residuals. Now, what is a classical arch 1 process? We would assume that our zt would be standard normally distributed, and sigma squared t is given by omega plus alpha epsilon t minus 1 squared. So note again here, you can pinpoint the sigma squared t, the conditional variance of the return process at time t, only having information up until t minus 1. And then if you have the knowledge of the parameters, you know exactly what's going to be the conditional variance in the next period. Now we move on into the properties of an arch 1 process. The first property is that as we are modeling something which is called the conditional variance of the return process, we want to assure that sigma squared t is strictly positive. And that is true if and only if you assume that omega, the intercept, is strictly larger than 0. Alpha can be 0, however, it cannot be negative. Now, these are important parameter constraints. So we cannot estimate an alpha of minus 0.3. This is not allowed in the framework of an arch model, as again, we need to assure positivity. And this is an essential parameter restriction. We cannot go with the arch model without those parameter constraints. The second important observation which we need to make is as follows. If you write down a usual arch 1 process and then you insert instead of epsilon t minus 1, your zt minus 1 squared times sigma squared t minus 1, again given by the arch structure, you see that essentially what the conditional variance of the arch model implies is that you have a weighted average of the past information when it comes to determining the conditional variance, as opposed to the sample variance estimator, where you would treat each and every observation in the past similarly. So the arch model gives more weight to the recent information rather than to the distant one. The more recent information receives the weight of alpha. The information 2 periods ahead would receive a weight of alpha squared. So this is the weight for the t-1 information, t-2, and so on and so forth. And also note that in the arch framework, as we discuss in a minute, we consider only alphas which are smaller than 1. The third thing which we would like to discuss now is the very important property, namely the AR1 representation. This representation is very useful as it allows us to derive a lot of properties of an arch1 process using the knowledge of the usual time series analysis and the properties of an AR1, for instance. In order to derive this representation, we will add epsilon t squared to both sides of the equation. And then we rearrange the terms. And now we will write epsilon t squared as an AR1 process with an error term which we would call nu. And nu t is given by the epsilon t squared minus sigma t squared. So now what we need to show that this nu t, this error term, is a white noise error term. And if that is the case, then we have just shown that an arch1 process can be written as an AR1 in terms of the epsilon t squared. And so we now go to the first property of the error term. So we need to show that this nu t is a white noise. Okay, which properties do we need to show? We need to have a look at the unconditional expectation of our error term. And in all of those derivations, we will always rewrite epsilons as the product of the z's and the sigmas. Again, we assume zt to be normally distributed. So you have expected value of the zt squared, then the expected value of sigma t squared minus expected value of the sigma t squared. This is 1. And so the error term is 0 in the expectation. Next, we need to show that the expected value of nu t and nu t minus j is 0 again. So remember, white noise process is not allowed to be autocorrelated in any shape or form. And therefore, we would go and again write down the definitions. And then we open the brackets. Now we insert the definition of the epsilon t. Again, we use the fact that the zt's are IATs, so they can jump out of the expected value operator in a separate expectation. And in expectations, those zt's, which are independent from each other as well, these are just standard normal variables, one of them individually, which have a unit variance, which implies with the 0 mean that the expected value of zt squared would be 1 exactly. And so if those all expectations would be 1, what you see here that expected value of sigma squared t and sigma squared t minus j cancels with the second term, and the fourth term cancels with the third term. And so we just shown that the expected value of the cross product is 0 as well. Now, finally, we go and have a look at the unconditional variance of our error term. So again, it is the expected value of the square minus the square of the expectation, which we just shown to be 0. So what we need to consider is the expected value of epsilon t squared minus sigma t squared, and all of that to the power of 2. And again, we open up the brackets. And before that, we insert the definition of the epsilon t squared. And now, before anything, we would put the sigma squared t out of the bracket. Do not forget that everything is to the power of 2. So we have the expected value of sigma t to the power of 4. And in the other bracket, which due to the independence of the zt squared, you would have the zt to the power of 2 minus 1. And this we can now simplify because we know all the moments of the normally distributed random variable. So you would have the expected value of zt to the power of 4 minus 2 times zt to the power of 2 plus 1. And what's the kurtosis of the standard normally distributed random variable? That is 3. This is 1. So you have 3 minus 2 plus 1. And all in all, you have 2 times the expected value of the sigma t to the power of 4. Now we can rewrite the expected value of the sigma t to the power of 4 as the expected value of epsilon t to the power of 4 divided by the expected value of the zt to the power of 4, again, due to the IID zt's. Again, we know everything about the moments of the zt. And here we have the 4th moment of our epsilon t. And this variance of our new error term will be finite as long as the 4th moment of epsilon t is finite. And so what we have just shown is that we can rewrite an ART1 process as an error1 process in terms of the epsilon t squared, and the error term will be a white noise error term under the condition that the expected value of epsilon t to the power of 4 is finite. Now, what does this condition bring to you? It brings to you the stationarity. So hence we know that our epsilon t squared, or equivalently ART1, is stationary under the usual condition for an autoregressive process of order 1, that the alpha coefficient in absolute value is smaller than 1. We now continue looking at the properties of an ART1 process. And now we will compute the unconditional variance of our epsilon t. So for the ART framework, what holds is that the expected value of epsilon t being zt sigma t expectation would be 0. Doesn't matter which kind of process do you assume on the sigma t, something which we have discussed just in the beginning. Now, the variance of epsilon t is therefore given by the expected value of epsilon t squared. And now, here we go with the error1 representation. So for now, assume that everything is nice and stationary, and we have omega plus alpha epsilon t minus 1 squared plus nu t. This is our error term. So we have omega plus alpha expected value of epsilon t minus 1 squared plus the expected value of our error term, which we've just shown to be 0. The stationarity assumption implies that the expected value, the unconditional mean of the epsilon, does not depend on t and always equals to the same quantity. And this allows you to rewrite this equation and combine the two terms. So again, we use the stationarity condition and replace the expected value of epsilon t minus 1 squared with the expected value of epsilon t squared. And the expected value of the error term is 0. And so our expected value of epsilon t squared times 1 minus alpha is omega. And so we would, what we will write very often, the unconditional expectations of our epsilon squared returns, basically, so unconditionally, without seeing any data or information, is given by omega divided by 1 minus alpha. The next property would be about the volatility clustering effect. Now, think about an R1 representation of our Arch1 process. The relationship which we have derived before, the unconditional variance of the epsilon t squared, or the unconditional variance of the epsilon t rather, allows us to write down our intercept omega as 1 minus alpha times the unconditional expectation of epsilon t squared. And now we can insert this definition of the omega into our R1 representation. We now rearrange the terms a little bit, and we carefully look at this, because this is nearly the property of the volatility clustering. So now we take the expected values of those terms. So epsilon t squared minus sigma squared epsilon given ft minus 1. Remember, our error term is just 0 in expectation. So remember, our epsilon t minus 1 is ft minus 1 deterministic. Using the same logic as we did above, we can write everything as just epsilon t minus 1 squared minus sigma squared epsilon. So at time point t minus 1, we actually do observe the epsilon t minus 1 in our data. And now, what is volatility clustering? How can we make our minds and formally characterize the stylized facts of the squared returns, that the periods of high volatility are followed by the periods of high volatility and vice versa? So if at period t minus 1, you had that epsilon t minus 1 squared, so your squared return, was larger than the sigma squared epsilon. Remember, by construction, our alphas are non-negative. This would imply, with the coefficient alpha, if this term is positive, then what we expect for the next day about the relationship between difference between epsilon t squared and sigma squared epsilon t. We expect it to be positive as well, as alpha is positive. Similarly, if the term is negative, then our expectation is negative. So what does it mean intuitively? If at time period t, the shock, the squared return was larger than its unconditional expectation, then we would assume that the next period, the squared return will be again higher than what it is expected to be unconditionally. Similarly, the periods of low volatility, so if the volatility is below its average level, then we would expect that the next period, we would again have a calm market. And the way everything decays, the way the new information decays is the alpha. So with the coefficient alpha, the higher the alpha, the larger would be the persistence of those shocks. So this is a shock, as this is the difference between the squared epsilon and its unconditional expectation. And if alpha is very, very large, this difference would propagate across time. For the smaller alpha, the memory of the process or the persistence of the process would not be that high. So this is how we formally show that yesterday's deviation from the mean explains today's expected deviation from the mean. Periods of high volatility are followed by the periods of high volatility, and the periods of low volatility are followed by the periods of low volatility. This property is known as the volatility clustering.
So putting this very simple kind of specification in the conditional variance process, we're able already to model volatility clustering effect, which with the assumption on the white noise is not possible. What else? We also remember that the second moment of the return process, what data tells us, has terrible amount of outliers. Nothing is distributed in any sense we kind of know. So what we can show is that the arch process by construction captures the over-kurtosis, that the kurtosis of epsilon t with the arch 1 specification would be larger than 3, and in order to do that, we need some derivations. The definition of kurtosis is as follows. You take your error term epsilon t, subtract the mean to the power of 4, divide by the variance to the power of 2. Now, from the properties of the error term which we have derived, we know that the expected value of epsilon t is 0, and the variance of the epsilon t is the same as the expected value of epsilon t squared. And now we're going to go step by step through all of these guys. So this, I'm just going to be lazy and write that this is sigma squared epsilon squared. And the whole headache comes from the fourth order. In order to proceed with the derivations, we need to remind ourselves that the kurtosis of a standard normal random variable is 3. And now we focus all our attention on this guy. We plug in the definition of an arch 1 process. And then we open the brackets. After plugging in the definition of epsilon t, everything is to the power of 4. Again, we remind ourselves that the kurtosis of zt is 3. And we can replace the sigma squared epsilon under stationarity. We now assume the same stationarity again and write down the expected value of sigma to the power of 4 as omega squared plus 2 omega alpha, and then the unconditional expectation of the epsilon squared, and we divide it by 1 minus 3 alpha squared. Okay, so then we need to go back to our kurtosis formula and plug it all in there. So we need to multiply this guy by 3 and then divide by the unconditional guy to the power of 2. We then need to plug in the definition of the unconditional variance. And after some immense amount of algebra, we will obtain the result. This is, of course, your homework. Now, what you arrive at is the following expression. So you have 3 plus something. Remember what we're trying to do. We're trying to say that the kurtosis of epsilon t under Arch1 specification is larger than 3. It is so if and only if this term here is non-negative. Now, alpha squared is not a problem. What you really need to assure is that 1 minus 3 alpha squared is larger than 0, and that would imply that the only acceptable region for alphas is from 0 to 1/3, and that is suboptimal because remember the persistence of the shock is also alpha, so you kind of want it to be large as well. What do you do? So if alpha squared is indeed in this very restricted region, then you are able to capture overkurtosis. However, it is a trade-off between capturing a lot of shock persistence and overkurtosis. So what does it imply is that the tail of epsilon t under Arch specification is heavier than of the normal distribution, and you could really model the dynamics of financial time series with this. What is important is that Arch1 is not able to capture any asymmetries on the market. Arch1 assumes a very sweet distribution on ZT, the normal one, which has no skewness whatsoever. And you could practice deriving this covariance and show that actually, because ZT is assumed to be symmetric, the covariance between epsilon t and sigma squared t plus 1, the famous leverage effect, is actually 0. Okay, so please do practice this. Just same business, insert the definition, plug in everything. But what you actually want this covariance to be, you want it to be negative. So if there was a very, very high negative shock, you want your volatility to be higher compared to the case when the shock was positive. That was the fact that we saw much more negative outliers in the return process rather than positive outliers. And the Arch1 is not great in capturing leverage effects. You need additional specifications there, and the reason for the Arch1 failure is the symmetric distribution on the ZT. Please do derive those on your own, okay? This is a good practice for your exam.